Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson, and we're going to be answering a question from a listener regarding the right liner to use for a centrifugal pump.
Now, you have to keep in mind that this came through a note on the NoMTBF site. So I'm glad people are still reading that and looking at it and stuff. That's way cool. And one of the questions that I know I can answer is, should I use MTBF or a different metric to help me sort this out? And so that was easy.
Okay.
But the hard part here is, right, so it sounds like he's trying to do some analysis on the set of products that they recommend and install in, I think it's in oil, gas fields areas, because it's, and I think it's in oil exploration because they're talking about different slurries. But I don't have a lot of details of exactly where they're at. But they have a pump, a centrifugal pump, and they put a liner in it to protect the metal from the contents of the slurries, which are usually acidic chemicals and either and abrasive. Abrasive and acidic, and it's either a slurry of some stuff, or it's a water-based system, or it could be some other chemical that's a liquid going through it. So it sounds like these are not your typical pumps to move water around for drinking. They have their own challenges. And they have a range of pumps, and then they can customize them with the liners that get put into them for uses in different sets of conditions. And they have a experience base of their team saying, oh, if you're in this environment, this kind of slurry, use this liner. And so what he is doing is saying, well, where's the data on this? What's the evidence of this? And they have field data. They have information about what pump, what liner, what environment it was in, what kind of slurries were being used. And then how do I use that data set to figure out what's the right liner to use given a particular slurry composition that's going to be used? Now that, well, one, don't use MTBF. And some pumps run to failure, some pumps run to a certain degree, and then they take a look at it and they assess whether they have to replace that liner or not for the next job, kind of thing. So they get some evidence of partial degradation, or it's holding up well under so many hours. So partially censored is kind of the way I think of it. And others had failed, so then they replace those and they have time to failure data. But they have lots of combinations, as you can imagine, different styles and sizes of pumps and different types of slurries. So it was, all right. How would you approach something like this, Chris?
Is the liner sacrificial?
It seems like it is. In some systems, it takes the brunt of this abrasion, so it wears, and the acid is what attacks the metal at some point in the seals. But I think it's a protective coating is the way my understanding of it is.
So if that's the case, then my preliminary guess at how the time to failure, which is time to the liner being worn through, would be modeled, would be with a normal distribution where the rate of wear or damage accumulation is consistent throughout usage. So that's the first thing. And that means the MTTF can be helpful to try and find the mean of that bell curve or that normal distribution. But then it would be up to, additional data analysis to characterize that bell curve as well. So if there is a substantial amount of data for that particular failure mechanism, I would first try and confirm through some sort of probability plotting that the normal distribution does the best job of modeling it, which I'd expect. And if it does, then use it to characterize time to, the L1 life, for example, where you'd expect a certain 1% of liners to have been worn through or suitably small percentage associated with your risk tolerance. And of course, if you see something besides a bell curve model, the time to that liner being worn out, then there's something very different going on, to the extent that I would be scratching my head as a reliability engineer.
Yeah, it could be difference in pressures, difference in and certain, different mechanisms occurring, not just this fluid flowing through it at a consistent pressure and rate.
Right.
Yeah.
So yeah, that'd be my first thing. If there's something going on, if it's not a bell curve, there's something else going on, to the extent I would not be able to guess. Yeah, what are your thoughts beyond that first
Well,
initial
my
stab?
yeah, my first thought was, right, it's similar to the last question is, well, what's the mechanism? What exactly is considered a failure? And what's the root cause analysis of that? And even in the question is, would an RCA or DAIMAC help me show the improvements? And it was basically, if I can predict the right liner for the right circumstance, how do I prove that it's better? Well, get enough data. It's one way to go at it. But another one is that if it had 100 hours versus a pump that was the experienced recommendation, and you can measure the degradation, say the thickness at a critical point on the system, which one held up longer. But see, I would go to the lab and I got 15 types of slurries, and I got 15 kinds of you probably need a grant and 200 grad students to do this study, I imagine. But um, I'd say let the field data guide you and look for why do the ones that just work, why is that? What is unique about those? Was it lucky happenstance or what? And I don't know enough about their policy of if they recommend one kind of, liner for every thing in a certain oil field and just make that decision once, or do they do it per well site? And I'm just assuming that it's an oil exploration. But the
Yeah.
part of it is, how is it decided now, and what's the basis for it? What's the science or engineering knowledge of that? Is it just anecdotal, or is it consistently repeatable and teachable to the people making those decisions? And if not, then go there first. What exactly is happening to these things? And why is it what is going on? Talk to the engineers that are designing these different liners, and then get information from those actual slurries to say, is this even close to what we expected? My few handful of times of touching oil at exploration type folks is that they're really smart. They know a whole lot of stuff about what's going on with their systems, and they're consistently surprised. The earth is in a horrible place to operate.
Yeah. Yeah, and I mean, I'm thinking of silly things as well. As what can you do to reduce the extent to which slurries are brighting away any liners? Can you do any sort of filtration efforts? And I'm sure people will be rolling their eyes, or
Yeah,
that's a
here's
question.
100 gallons a second, and it's this, and the slurry is made. It's the stuff coming out of the well. Say, for example, it's the idea of the pump is to get it to where we can separate it.
Yeah, absolutely. And I think when it comes to selection, yeah, the good thing about wear, which I'm guessing it's sacrificial, and so the wear is somewhat uniform. You should be able to do, yeah, like you mentioned, some laboratory stuff.
Yeah, it's what is the and I had it drilled into me years and years ago. Is go back to first principles. What is actually happening? What is the nature of the abrasion? Is particle size really a factor, or is it more the speed or the pressure? Or is it the type of a material that's coming into it? Is it silica based, or is it some other material that doesn't have the sharp edges? There's as sharp edges, and so on and so on. And taking a look at, can you get some models together that replicate the data you're getting in the fields? Because you may be making choices that are blind to a couple of options that would optimize the system. And so design of experiments type stuff to figure out what is the right combination for these different circumstances. And it's got to be robust enough for all the unknowns in that particular environment. So I think the saving grace with this one, unlike the last one, is that it sounds like there's more data. Yet I fully
Yeah,
suspect it's very noisy.
yeah, which is the challenge. But the question, though, as I recall, is how do you select the right one? Is that correct?
Yeah, it's a predictive question. How do I
Yeah.
set it up correctly so that they get the maximum runtime for that pump?
Again, that would just it would have to come down to the ability for that liner to resist being worn away. Bell curve would probably model it. I'm not. Again, the good thing was that you'd imagine that you'd be able to replicate fairly easily a laboratory analog to that scenario. I would guess, which means that it can be pump agnostic, which is essentially what you want.
Yeah, I'm sure there's more to it. And looking at the question, and the very last one is, even though I'm saying if we can get the right liner for the right circumstance and it runs for twice as long, we don't have to repair it. We don't. So he's getting resistance from inside the company saying, well, then we only sell one pump. And the customer is going, just bring extra pumps and keep it going. And
Right.
it was the, this is the way we always do it kind of mentality is getting pushback on it. At least he asked about MTB up and said, I don't think that's the right way to go. So I concurred with that. But you're right.
Right.
If it is normal, you can get one of the two parameters just with that. But if you got time to failure or runtime data on these things, then use that. Don't dumb it down to just counts. But my approach was segregate out what you have, clean up the data as best you can, get the graphics, use red, yellow, green if you have to for managers, and let the data talk. Yet the better you and your team are at articulating the chemistry, the mechanics, the fundamentals of what's actually occurring with these different materials sets that you're dealing with, the more plausible that approach is versus, well, in West Texas, we always use blah, blah, blah. I'm like, well, how's that working for you? Here's the data. East Texas is doing way better than you are. But that won't work here. I says, you're right. But what you got now could be better. And I think that's where part of the argument is the analysis has got to get past those hurdles of resistance of that's not what we do here.
Right. And yeah, again, it's just an inquisitive mindset, I'd imagine. I don't know. Have we come close to answering the question, well, how do we select the right one beyond just simply either testing until it wears away or creating a laboratory condition?
Not really. It's a data analysis, and then I'd say the physics of failure type understanding of it, of what's going on between those two. I think you can then get some evidence that there is a better way to make those decisions. And and I see that. I probably have done that kind of an analysis before. It's
Mhm.
my own experience though in oil and gas is as soon as you punch a different hole, even if it's 20 feet away, and I'm just making the assumption that it's an oil and gas. I have no idea. Um,
Mhm.
in oil exploration. If you punch a hole 10 feet away from where you did the last one, some portion of what you learned in that first drill applies, but some things don't. It will be different.
Right.
This the nature of the Earth's surface and crust is that it's different in different places
Mhm.
and it affects your equipment in different ways.
The other thing too is that if it's being worn away at a consistent rate, you don't need to test liners until failure. All you need to do is test materials and measure the
Yeah,
rate at which material is being degraded away. So that shortens testing duration considerably. As
yeah,
in, I'm not sure what liner thickness is. Let's say it's 10 millimeters. You don't need to wait for everyone to have been worn all the way through, have 10 millimeters worth of material worn. Like, that sounds like a very thick liner. But just
yeah.
for argument's sake, all you need to do is test comparable materials, and it would
Measure it
be the
every day,
run.
and yeah, what's the rate
Yeah,
of rate of wear?
yeah, and so they all might still be working fine, but you might be able to identify which one is wearing away the most, or the fastest, or the least quick.
The least
And that
quick,
would
yeah.
be the
It's a technical term. I haven't heard in a while.
the least quick. Yeah. And that would then essentially shorten the test duration you need to identify the optimal material.
There may be an opportunity here, Chris, for us to come up with a material that takes a little bit of wear, but because of the wear particles, then do a cross link or do some other phenomena that doesn't heal it, but slows the rate of wear. I'm thinking of like a copper oxide. When copper rusts, I think is the technical term for it, it turns green. And architects seem to like that for some reason. But it also stops the degradation of the base material. It prevents the oxygen from getting in, going further into the core, into the material, unlike iron, which will just keep eating away at it until it's all gone. So is there a liner that can react to the material that's eroding it and counter it? Now that would be a cool patent.
Oh, that'd be a challenging mechanism to develop.
Well, that's why it's $1 million idea. You can have that one free, Chris. Free. Run for it.
Oh, I mean, well,
Put
if
me in
that's
the
the case,
footnote somewhere.
I have lots of $1 million ideas then. But if
Yeah. Now, I do know that, pumps and liners and harsh materials going through and it could be in the wafer fab process. There's some really horrible chemicals being moved around in those things to where I I got introduced to a pump that the way the pump worked, there was a material or liquid or air, it depended on what was actually being used, that prevented the material they were actually moving, this acidic type thing, from ever touching the pump. It just never
right.
actually came in physical contact with it because they also had this envelope around it that kept it contained away from the materials, the surfaces of this pump. And I thought, well, that's clever. And they wanted to know if I could set up a test lab in California and test it. And I looked up the material and says, I don't think California allows you to have this within 2,000 miles of this state. So I doubt I can have it here. So at that point, I was out.
Right.
I mean, part of it, the answer is part of it is the data analysis is a piece of it. And I think it's a more general question is, well, how do I make that convincing? And it's back to where's the value? How does it actually benefit the company and the customer? And so we both win and stay profitable. We still accomplish whatever the mission of this pump is in a more higher uptime and more efficient way. Um, all of those kinds of things. And then you layer over it that there's a bunch of unknowns, and we may not know exactly what it is that makes the one liner wear differently than another one. So I'd go back to the lab, use the data as a starting point, use the lab to confirm those models, and then go forward with that. It's kind of been my advice on it.
Mm-hmm.
And get real good at PowerPoint.
Yeah. So if the question is which one, how do I pick the right liner material? Well, step number one is understand you'd expect to see it being worn away at a uniform rate, and so by extension, if you do have failure data or wear out data associated with that liner, try and model it and see if it's got a bell curve. If it doesn't have a bell curve, then they need to let us know because we need to have another chat about it because that means we don't know what's going on.
Yeah.
Yeah, if you do see a bell curve, that's great. That means that it aligns with how we think it should be being worn out. And so once that happens, then again, your options are put various materials in a pump and just test, or recreate conditions in a laboratory where you don't need to test until the thing fails. You just need to see which material gets worn away the slowest, and that's potentially going to be the right one to use. Yeah, so I think that's as far as we can go. Have we missed anything?
Yeah, no, it works for me. I hadn't thought about if it's normal or not. I hadn't thought about that. So I'll send Pierre, who asked the question, I'll send back that note. And I tell him that we talked about it for a few minutes and it's kind of more vague, maybe or maybe not helpful, but hopefully helpful. And we'll go from there. But No, it's one of a handful of questions that we've gotten lately, and I'm happy to get more of these this year. I think we've set a record here in the first quarter of the year with the number of comments and questions we got that we brought into the show. So I'd like to keep that going. So if you're listening to this, you know what I'm going to say is let us know. Send us your comments and questions, and we'll get you an answer or direction or some input back, but then we'll probably talk about it. Maybe get you a better answer as we often do. So let us know. Head over to accendoreliability.com/go/SOR. You can find a couple of ways to get in touch with us. Chris and I and the other hosts are available through LinkedIn and our About pages, and even the nomtbf.com site. I get those comments and questions. So there's yet another way you can join the conversation. So we look forward to hearing from you. And with that, Chris, put our pencils down and call it a day.
As always, it's always a pleasure.
All right. Thanks, Chris. Talk to you soon.
Cheers, Sion.
Cheers.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.